Hello, everyone. What I want to do now is essentially summarize and continue on from what we did last time in the following theorem, which I'll now prove. We proved half of this already. So let's say X is a normed vector space. Okay. Then there exists a Banach space X star where the following is true. As we explained last time, X embeds into X star isometrically, rather densely, meant to say densely. And what does that mean precisely? There exists a map, a linear map from X to X star, linear, and it's isometric, meaning that it's norm preserving. So phi, the norm of phi of X is the norm of X for any little x and big X. And last but not least, this is a dense subspace of X star. Okay, so practically speaking, yeah, X, basically, you can think of X as itself almost a dense subspace of X star, because this map here is linear, it's isometric, hence it's obviously injective, and this is dense. The image of X is dense in X star. Okay, so we proved one already. Okay, and any such Banach space X star is called the completion of X. Okay. And I should mention there's not one single way to do this. I think the way we did it is probably the easiest way, or probably the most natural way to do it. In particular, I think really the only easy way, or the easiest way rather, to define the real numbers from the rational numbers is to do exactly what we did, to define the real numbers as the collection of all equivalence classes of Cauchy sequences of rational numbers. There's really not an easier way to define the real numbers from the rational numbers. I mean, usually we don't bother doing that, writing down the details, just because there's not enough time. But yeah, that is really the canonical way to define the real numbers from the rational numbers. So basically, what we proved last time is that this construction works for any normed vector space, which is pretty remarkable in some sense. And I claim next is that I'm justified in saying the completion, even though I just said there's other ways to do this. There are other ways to construct an X star where this is true. Despite that, this is more or less unique in the following sense. given any two completions, so given any two Banach spaces, x1 star and x2 star, satisfying, make it a little neater, there exists a map from x1 star to x2 star that's linear, surjective, and isometric. So in other words, this map here is norm preserving, and it's an isomorphism as it's an isomorphism from these two vector spaces. So in other words, x1 and x2 are basically the same. They're isometrically isomorphic. They're basically the same Banach space in some sense. So then in that sense, the completion is unique. However you want to construct this X star, any two constructions are going to be isometrically isomorphic. Okay, so proof. How do we prove this? Okay. So let's first, well, before I prove it, I want to just draw a diagram to kind of keep our heads straight. And I'll continually update the diagram. So we have X here. And we have two Banach spaces satisfying one here. So we have two maps. So first of all, let me get rid of this here. Well, so I'll just leave everything alone. So we have two Banach spaces, x1 star and x2 star, and then we have these maps, phi1 and phi2, that take x into x1 star, respectively x2 star, where phi1 of x is dense in x1 star, phi2 of x is dense in x2 star. Okay, so right, we have phi1, phi2, both of them are norm preserving, they're isometries. And our task is to prove that we can find this map from x1 to x2 that's also going to be norm preserving, and it's going to be surjective, and it's linear. Okay, so the first task here is to construct this map. And that's pretty straightforward. So this proof is a bit long, but each step it's really not hard. It's just, there's a lot of tiny little moving parts. None of these moving parts particularly too deep. So it's a bit of a pain in the ass, but it's not a hard proof really. Okay, so how do we construct this map here? Well, let's start off with x hat and x1 star. Okay, so this is dense, the image of x under phi1. So pick sequence xn. Where x hat is this limit here. So I should really emphasize that we don't know what x1 star and x2 star are. We know nothing about these Banach spaces other than one is true for both spaces. So we have these isometric embeddings, phi1 and phi2, where the images respectively are dense in x1 star and x2 star respectively. All right, right, so phi 1 xn. Okay, so easy thing. So I claim in particular that phi 2 of xn is Cauchy. So if it's Cauchy, then it'll exist because, well, I mean, obviously, this is a subset of its sequence in x2 star. X2 star is a Banach space. So it converges. And it converges to something in x2 star. Okay, and this proof is very easy. Right, so let's just write down what this is. Phi 2 of xn minus phi 2 xm x2 star. Well, this is linear. So it's phi 2 of xn minus xm. Well, it's norm preserving, so this is just xn minus xm x. Well, it doesn't really help us all that much just yet, but we also know that phi 1 is norm preserving. And it's linear. So let's do the usual song and dance here. Let epsilon be positive. Pick n or nm bigger or equal to n implies, well, we know this is convergent. We picked it to converge to x hat. So it's Cauchy, phi 1 of xn, the sequence. So this here is less than epsilon. So pick n where this is true. Again, phi 1 of xn is Cauchy. Well, this literally is equal to phi 2 of xn minus phi 2 of xm x2 star. So that means that this is less than epsilon, and hence, right. So put this in red to emphasize what we just proved. Yeah, these two are equal. So this is less than epsilon, and so is this. And hence, that finishes the claim that we have a Cauchy sequence. Okay, and again, x2 star is a Banach space, so the limit exists. So define this map here to be this limit here. Phi 2 of x n. Okay, so that this is an x2 star. So homework is that this is well defined. It should be clear what you know that we do need to prove that it's well defined in the sense that this map does not depend on the sequence xn chosen as long as xn is chosen in this way. So I don't care if I do use xn or some other something else, doesn't matter. As long as this is true, then homework is this, this limit is going to converge to the exact same thing, no matter what sequence I pick, as long as the sequence is picked to satisfy what's in the green. Okay. Okay. So let's prove that this is an isometry. And this is pretty easy. Everything's pretty easy except proving that this is surjective, which we'll do by constructing the inverse. That is a bit of a pain. It's quite a bit of, it's really painful. And not that painful, but it's a bit of a pain. So, okay, right. So there's really nothing all that much to this. Let's just do definition chasing. Okay, so this is going to be equal to well, sorry, I need a limit here. Okay, so because we have phi 2 of xn converges to psi of x hat, the norms converge. Well, this is norm preserving. From x to x2 star. So it's just xn, x1 star, sorry, just x. But again, so is phi 1. And you should know what this limit is going to be. Well, phi 1 of xn converges to x hat. So the norms also converge. So this is just going to be equal to x hat. Okay, so that finishes up this claim here that this is an isometry. Well, the fact that it's linear is pretty straightforward. There's really not much to that, so I'll leave that also as a homework. Okay, so right, so let's repeat this process. So let's see what we've done so far. So I have this map here that at the very least is a linear isometry. So we need to prove that it's invertible. And actually, interestingly enough, we're going to, but to do that, we're going to prove that this diagram commutes in the sense that Well, I'm going to basically just reverse the construction of what I've done. Basically, exact same thing, just swap x1 star and x2 star. So I'll get this new map. I'll write everything down. Psi tilde, reversing this process. I have nothing, I don't know what else to call it right now. So, but if I swap the roles of x1 star and x2 star, I'll get this map here, and I'll prove, and we'll need this, I'll prove that this diagram commutes in the sense that phi2 is given by psi composed with phi1, and phi1 is given by psi tilde composed with phi2. All right, so yeah, my next task is to construct this map here, and I want to prove that this is going to be the inverse of phi. Right, so, right. All right, so yeah, let's start proving that this map is invertible, which is basically what we have to do to finish the proof. So, right, swap x1 star and x2 star, and repeat. What do I mean by that? Well, let's say y hat is now an x2 star. Define this new map in basically the same way. Define it as this limit here. Well, now use phi1, okay, where here y hat is this limit of phi 2 of xn for xn and x, well, xn and x. Okay. We know such an xn exists because phi 2 of big X is dense in x2 star. Okay. Again, x1 star and x2 star both satisfy 1. Okay, so we're going to use every little bit of, we're squeezing every little bit of information from 1. We're going to need everything for both x1 star and x2 star. Okay, so if we do that, right, exact same proof tells us that, well, first of all, this sequence right here in red is Cauchy. Literally, the exact same proof tells us that this is Cauchy. So this limit exists because x2 star, sorry, x1 star. x1 star is Banach space. So, right, so this thing here lives in x1 star. Again, this is a Cauchy sequence by exact same proof as what we had a moment ago, and hence it converges, the limit exists, it converges to something in x1 star. Okay. So this here, it's linear and it's isometric. So I just write it down. So, right, so x1 star is going to be the norm, x2 star. Okay, so I claim, so let me just write, so what we at least now have is we at least now have these two maps, two norm preserving maps, one going from x1 star to x2 star, one going from x2 star to x1 star. Okay, so I claim that, right, well, I claim that this is the identity. It's the identity map. Or let me maybe let me write it like this. So I claim that this is the identity map. Not on x1 star, but at least for now on the image of x1. Okay, and this is really just definition chasing. Why is this? Well, let's just unravel everything. So let's say x hat is phi 1 of x. X and big X. Make that a little neater. Okay. Right, so just to make sure we have our head straight, so I'm going to do this very slowly and carefully. So if xn equals x for all n, all right, so what's this limit here? Well, this is pretty trivial. Xn is x for all n. And this is exactly what x hat is. X hat is phi 1 of x. Okay, so remember, what does this mean? Well, we defined this map here, psi. By definition, this is going to be, well, the exact same thing as this, just erase the 1 and stick a 2 there. Okay. Now remember, it's independent of how we approximate x hat. As long as xn satisfies this here, doesn't matter what xn is, you know, this map is defined in the exact same way. It's independent of the sequence xn. Okay, so in particular, well, what is this? This is going to be psi 2 of x. All right, so I'll put this in orange here. It's more of a mustard color, but anyway, whatever. All right, so let's try the same game with psi 2. Right, so 1 second. Right, so let's say y hat is phi 2 of x. And again, let's say xn equals x. I'm just doing this just to really emphasize that I'm just doing nothing but the definition of the maps we're constructing. Whoops. All right, so for any natural number n, okay. All right, so right, so phi2 of xn in the limit, well, that's literally just phi2 of x, and that's y hat. So by definition, well, actually, really, yeah, I'll just write it like this. Okay, so this converges to y hat. So again, by definition, doesn't matter how I approximate y hat, this definition is independent of the xn chosen as long as this here is true. So this, by definition, is going to be same thing as this, but just switch, going back to the definition here. There we go. Right. Something I had in green before. So let me get rid of all this crap here. I don't know why it doesn't want, there we go. Right. Okay. So this is going to be equal to phi1 of xn. Well, and that's just phi1 of x, right? So put this in a mustard color here. And actually, really what I want, so maybe I'm going to have to move this, yeah, so really what I want is following. So let me just rewrite this, make it a little smaller. So really what I want is psi tilde of phi2 of x. Well, by definition, said y hat was phi2 of x. All right, so here we go. All right, so let's put all this to good use. Okay, so psi tilde of psi of x hat. All right. Well, what did we conclude that psi of x hat was? Well, it's phi2 of x. Kind of see where this is going, I hope. What did we conclude that psi tilde of phi2 is? Phi1 of x. Well, all we did was we called x hat phi1 of x. We just said, well, pick an x. Pick an x and big X, and let's say x hat is phi1 of x. Pick an arbitrary element in the image of x under phi1. So that proves the claim. Okay, so finally we claim that psi tilde, psi of x hat equals x hat for any x hat in x1 star. So obviously that means, well, psi tilde is psi inverse. Okay, and the proof is actually pretty straightforward now. Basically, because we have an isometry and we have what we want on a nice dense subspace at phi1 of x. Right? All right, so let me fill in the details. So let me actually use composition notation, otherwise your head's going to spin. So many maps. Okay, so let's just use a triangle inequality. So in particular, let's say phi1 of xn is x hat. Again, for probably the sixth time, phi1 of big X is dense in x1 star, so I can always pick an xn in x1 star, xn in x, where this is true. X hat is in x1 star. Okay, so, whoops, sorry about that. Right, so let's, actually, that doesn't make much sense. I'm going to add and subtract that. So let's subtract it. And we're going to use everything we've basically proven so far to show that this has to equal 0. And this is x1 star, phi1 of xn, plus, well, don't have much choice now, so you have to add it. Now let's call this A plus B. And here, we're going to let n go to infinity, but we'll do that in a moment. Okay, so A is going to be this here. Let's use the fact that this is, both are linear, so you compose linear maps, it's linear. So this is going to be psi tilde composed with psi of x hat minus phi1 of xn. Well, you compose two norm-preserving maps, you get a norm-preserving map. So this is just going to be x hat minus phi of xn, x1 star. And lo and behold, that converges to 0 as n goes to infinity. Just because we picked xn in this way. So not much there. Phi1 of xn converges to x hat. Okay. And B, we're going to do something a little different here. Remember what B is. B is psi tilde composed with psi of phi1 of xn minus x hat. Well, you should know how to handle this. Remember, well, this here, right, so we proved just a second ago, maybe more like 5 minutes ago, we proved this exactly right here. I'll put it in blue here. So I'm going to use this. So in particular, certainly this is true where x hat equals phi1 of xn. So here x hat equals phi1 of xn. Okay, so just go back here. Well, so this is just the identity. Well, maybe I shouldn't write that. That's maybe a little confusing. But anyway, the point is on the image of x under phi1, psi tilde composed with psi is the identity. So this is going to be equal to keep it blue, well, just phi1 of xn minus x hat. And again, this converges to 0. All right, again, psi composed with psi. I'll write it a little differently. Exactly what we proved before. This equals phi1 of x for any x and x, big X. This here let me do that. So what I'm putting in a circle here is exactly the same thing, when you think about it, as what I have here. It's exactly the same thing. Okay. Literally is the exact same thing. All right, so this here is just phi1 of xn. So that finishes the proof. Okay, so yeah, to finish this video up, I want to state the following proposition, which will be a homework exercise. And that's if X is a subspace of Y, X and Y are normed vector spaces. If Y is complete, and X is dense, and Y, then Y is the completion of X. Again, in the sense that Y is isometrically isomorphic to any other completion of X. Okay. Okay, so for example, so however you so desire to define the real numbers from the rationals, this proposition tells you that because the rationals are dense and the real numbers, so sorry about that, I meant to put the reals. Right, so because the rationals are dense and the reals, this is the completion of the rationals. Okay, likewise, we know what the completion of the example I talked about at the beginning of the last video, that's just ordinary LP. Okay, so LP on -1 to 1 with the usual LP norm is the completion of C -1 to 1, P -1 to 1. Because, well, continuous functions are dense in LP. LP, we know, is complete. So, right, completion is unique. So, as I said, last video, we'll talk about the Sobolev space and the homework, where basically you take the space of all continuous functions on -1 to 1, open -1 to 1, where these functions have k continuous derivatives, k bounded and continuous derivatives on -1 to 1. And with this LP norm, with the LP norm applied to f and all of its derivatives, basically, essentially, you complete that, you get what's called the Sobolev space. I'll talk about that in the homework, but it's a beautiful example of a completion, and you can basically identify what the completion is. But anyway, that's for next time. So, and next video is just going to be more mundane Hilbert space stuff that, as I said, I'll try to go quickly through. All right, so long, take care, bye-bye. Hopefully this was interesting and informative.